The binomial distribution. Suppose that Matt can complete 80% of insanity workouts without stopping. How does this scenario resemble a binomial problem? Feel free to pause the video and answer this question yourself. The main thing about a binomial problem is that there are two outcomes. So, one of the outcomes we refer to as success. So, binomial means two outcomes. One of the outcomes we call success. And in this case, the event success would be Matt completing the workout without stopping. Completes the workout without stopping. And so failure would be that Matt stops at some point in the workout. And still complete the workout, but at some point he has to stop and catch his breath. Those of you who have done insanity probably know how successful it is to complete the workout without stopping. But that's the binomial part. The binomial part is the two outcomes, success or failure. There's nothing else that can happen in this situation. So the other thing is that with the success, there is an associated probability, and the chance that Matt completes the workout is going to remain constant because these trials are going to be independent of each other. So the chance that he completes the workout, the chance of success, which we call P, is 80%, and the chance of failure, which is the complement, and sometimes this will be referred to as Q, that's 20%, 0.20. And so this is how this problem is binomial. What we would also look out for, which it doesn't have it just now because I kind of stopped the question before posing the question involved, but we would also look for a particular number of trials, which we call N. A particular number of trials. We don't see it yet, but we'll see it in the next frame. And then you're also going to be, the essence of a binomial is you're going to be counting how many successes a particular number of successes out of how many trials. Particular number of successes. So we'll see this. But right now, the success or failure is the big part of the binomial. So here we get the rest of the problem. Here's the setup that we had. Matt can complete 80% of insanity workouts without stopping. But here's a little more now. Out of 20 randomly selected workouts, how many of them would you expect Matt to complete without stopping? So first, let's get familiar with the setup. If he completes 80% of insanity workouts, take a moment to reflect. Out of 20, so this means N is 20, so our N is equal to 20. And remember, our probability of success is 80%. So think about it. How many would you expect him to complete out of 10 trials? Out of 10 trials, I would expect him to get 8 of them, because 8 out of 10 is 80%. So out of 20, I'm going to expect that he's going to get 16 workouts. And remember, the expected workouts complete. So the expected value is also the mean. And the mean of a binomial distribution, what you did to get that 16 is you just multiplied the 80% times 20. Out of 20 workouts, you expect him to get 80% of them, and that's going to be 16 workouts. 16 successes is going to be, or 16 successes would be, again, complete workouts. And that's in a binomial. Anytime you have a binomial setup, Anytime you want to know the expected value or the mean, it's always the number of trials times the probability of success. That's going to tell you what is most typical in this experiment. There's also the standard deviation. So how does that typical value vary? It's the square root of n times p times q. And so in this situation, it's going to be the square root of n is 20, and the probability of success is 0.8, and the probability of failure is 0.2. And so that will now be approximately 1.8. So remember that these formulas for the mean and the standard deviation, these two formulas are unique to the binomial distribution. You can't use these formulas for any other distribution, and they will always work when you know you're in a binomial situation. So keep an eye out for those. So now let's take the problem to another level. Matt completes 80% of insanity workouts without stopping. Now, what is the probability that out of 20 randomly selected insanity workouts, he completes exactly 15 without stopping? So again, from the previous setup, we know that we're looking at 20 trials. Our probability of success is 80%, and our probability of failure is 0.2. And now we want to know the probability that out of 20 randomly selected insanity workouts, the number of successes, which we refer to as x, the number of successes is 15. So there's a couple of ways to do this. You can use what you know about probability. You know that you need to have 15 successes. So that probability of success, that 80%, has to happen 15 times. And if you've got 20 trials, how many times does failure have to happen? Well, if success is happening 15 times, you'll have to have failure happen 5 times to get a total of 20 trials. But remember that this is saying that the first 15 insanity workouts were completed and the last 5 were not. And there's other ways to get 15 completes and 5 failures. You can mix them up. These could be at the end. These could be at the beginning. So we know that 20, choose 15 on our calculator will give us the number of combinations of ways you can get 15 successes and 5 failures. Of course, my daughter is going to cry now, so please hold. Another way to complete this probability on your calculator, if you're finding the exact number of successes in a binomial distribution, is your calculator has a function called binom PDF. And the inputs are the number of trials, in this case 20, the probability of success on any given trial, and then exactly the number of successes you're looking for. And so that would give you the same result. And what is that result? Good question. Oh, by the way, while I'm calculating this result, the binom PDF doesn't make your instructor, if you have Angie, as happy as the formula. So if you want to make me happy, show off what you know up here. But this will be acceptable as well. So we've got 0.8, 15, just something about it, about that formula that I think makes sense and I like to use. So the answer to this would be, there is a 17.5% chance, so 0.175, or 17.5%. And does that make sense? That is a likely event. It is not an unusual event. And remember what we said earlier. Here, what's the chance that he completes exactly 15? Remember that we expected him to complete, from the previous slide, we expected him to complete 16 workouts. So would 15 be something that we'd expect to see? Sure. And the probability corresponds to that instinct. So notice if you also do the binomial PDF, you'll get that same percentage. So again, now we want the probability that out of 20 workouts, Matt completes less than 11. So again, I've got my same probabilities of success and failure, and I'm looking for the probability that the number of successes is less than 11. So before we go and compute this probability, again, remember, we expected, let's put our mean over here, we expected the typical number of times out of 20 that he would complete the workout to be 16. And our standard deviation, I can't quite remember, but I think it was around 1.8? Bueller, help. Yeah, it was 1.8. So we expect Matt to complete typically 16 workouts, give or take, 2 of them here or there. So would less than 11 without stopping, would that have a big chance of happening or a smaller chance of happening? And when I'm looking at these numbers over here on the right, I'm thinking that less than 11, which would be 10, 9, 8, or less, that's not going to be as likely to happen as the other values that are near 16. So what we need to use on this, because we're talking about, if we think about all the number of successes, so if we, less than 11, let's put 11 here, 12, 13, and then we've got 10, 9, right? Like we said earlier, less than 11, does that include 13? No. Does that include 12? No. Less than 11, does that include 11? No. Less than 11 includes 10, 9, and everything in that direction. Okay? And then, please ignore the screaming in the background. That's a 5-year-old. And so, anyway, the probability that she completes 10 or less, we're going to need, that's a lot to count, so we're going to need the binomial CDF. But the first thing I'm going to do before we use the binomial CDF is we need the upper bound. Notice 11 is not the upper bound for all of this data. Actually, 10 is. So the probability that Matt is successful less than 11 times is the same as the probability that he's successful 10 times or less. And this is going to be binomial CDF, hold on now, binomial CDF 20, 0.8, 10. As soon as we've got that less than or equal sign here, we know that that's going to be our input for the upper bound in our binomial CDF. So when I do this in my calculator, and enter 20, 0.8, 10, I'm going to get a probability, of 0.0026. So that's a very, very slim chance. Only 0.26% of the time will Matt complete less than 11 workouts out of 20 without stopping. So now they're asking, what is the probability that out of 20 randomly selected insanity workouts, Matt completes more than 15 without stopping? So think about this. More than 15, let's see, 15's here, 16, 17, 14's below it, 13, and so on. More than 15, 13 isn't more than 15, 14 isn't more than 15, even 15 isn't more than 15, but 16, 17, 18, and so on, right? These are all more than 15. So remember, we expected that Matt would complete 16, give or take 1.8 without stopping. And so these numbers, 16, 17, 18, they all seem like things that are pretty likely to happen. So I'm thinking that the probability that the number of successes is more than 15, I'm thinking that that probability is going to be pretty big. It's going to be pretty likely that he's going to complete more than 15 of the 20 workouts without stopping. The problem, though, again, we're looking at a range a lot to do exactly 16, 17, 18, 19, 20, and then add them all together. That would take a little bit of work. So we're going to, again, use the CDF function on our calculator. But the problem is that our binomial CDF is always, if you input your N, your P, and your K, it's always going to give you the probability that X is less than or equal to that upper bound. And what the problem is that 15 here is not an upper bound. What's the upper bound? The upper bound is 20, way on the right here. But if I look at this also, notice I'm not going to put in 20 because that's going to give me a probability of 1. The chance that Matt does at most 20, that's going to be everything. But what I'm going to notice here is that I've got the complement to this event. The complement to 16 or more is going to be 15 or less. So I'm going to take 1 minus the complement of more than 15 is going to be X is less than or equal to 15. That's the complement. And so from here, once I realize that's the complement, this less than or equal to sign is perfect for using this binomial CDF function. So to continue this, I'm going to have 1 minus binomial CDF. Let me erase. Oh, let me get rid of some of this stuff. Maybe I can't. I'm going to get rid of that so that it's not in your way. So 1 minus binomial CDF. And again, my inputs are going to be 20.8, and now my upper bound of 15. So when I input that into the calculator, binomial CDF is going to give me 0.3704. And so the probability that Matt's going to complete more than 50 workouts is, again, pretty big numbers, about 63% of the time. So forgive me, this is, for not writing my answers in a complete sentence. You should be able to do that, but I'll maybe do that in another video. Just to try another setup, suppose Angie can complete 65% of Insanity workouts without stopping. Now, we know this is fiction and that Angie can complete all of them without stopping, but, let's just pretend. But 65%, so in this case, my probability of success is going to be 0.65, and then my probability of failure would then be 1 minus that 0.65, and that'll be 0.35. So I have a 35% chance of stopping during a randomly selected workout. In this problem, we're looking at out of 10 randomly selected workouts. So my N is going to be equal to 10. So again, remember, let's think about our mean, and even though they don't ask me, let's think about what we would expect. Out of 10 random workouts, you'd expect me to complete, between 6 and 7, 6.5, because 65% of 10 would be about 6.5. And then that would be, give or take, the square root of N times P times Q. So N times 0.65 times 0.35. And that's going to be 1.5. So Angie's going to complete, I'm expecting 6.5 of the 10 workouts, give or take 1.5 of them. So I wouldn't be surprised if she completes 9 of them, and so on. So we want the probability now that I complete exactly 5 of the 10 workouts. And I'm looking at this, I'm expecting 6.5. So 5, wouldn't be all that unlikely. So I'm going to expect a pretty good chance of that. So I've got, out of the 10 workouts, I've got to have 5 successes. So the 65% has to happen 5 times, and the 35% has to happen 5 times. And I are 10 choose 5 ways of doing that, which comes out to a probability of 0.154. So a 15.4% chance that I complete exactly 5 workouts out of 10. Again, you could have also gotten the same answer with the binomial PDF. Is that what it is? Binomial PDF. 10, comma, your probability of success is 65. and then you're looking for exactly 5 successes. That would give you the same answer. So again, what is the probability now that Angie will complete at most 3? So I'm looking at the probability that I'm going to complete at most 3. Remember, here's 3, 4, at most 3 means 3 or less. So we're looking at these values here. These values on this side do not fit the scenario of at most 3. So we're looking for the probability that x is less than or equal to that upper bound of 3. And remember all of our data we've got, or all of our facts here, we've got probability of success is 0.65 and my n is 10. And so think about it also. Remember we expected 6.5 successes, give or take 1.5 successes. And so now we're looking at most 3. So automatically I know that 3 is kind of away from 6.5. So 3 and less than that, each of these, the chance of 2 workouts being completed is a little more unusual than the 3 and the 1 and so on. So this is going to be kind of a smaller probability, because I would expect the results to be closer to 6. So again, we're going to use binomial CDF because we are set up and ready to go with that less than or equal sign. We've got our upper bound. Binomial CDF, n is 10, p is 0.65, and the upper bound is 3. And when we enter that in our calculator, I don't know why I erased it, 10, 0.65, 3. We get 0.026. So a 2.6% chance that happens. Again, low probability. That's what I was expecting because I knew that 3 was a little bit of a ways from the 6.5. Last one, a common problem you'll see, a common question with binomials is what's the probability that I complete at least one? The at least one question is pretty typical. And again, we look at all our possibilities. I could complete no workouts out of 10. 1, 2, 3, 4, and so on, right? And at least one is telling me 1 or more. So all of these values, on and on and on. The only one that's not in at least 1 is 0. So this is a situation where, again, it's easier to look at the complement. So the only thing that's not in our event, 1 or more, is 0. So let's calculate the probability of me not completing any of the workouts, which we know is going to be really, really low. So the probability that x equals 0. And the only way that can happen is I have to have failure 10 times. And when I do that, I get, and then I take the complement, 1 minus that, it's going to be a pretty good chance that I'm going to complete at least one workout, right? The probability that x equals 0, this is really, really small. So when I take 1 minus something small, I'm going to get something pretty big. And it makes sense that I am going to complete at least one workout. I would not be happy with myself if I didn't. So hope that makes better sense for the binomial.